Hi everyone, today we are going to talk something about the distance between two sides. The distance between two sides we can form in a norm formulation. The distance between C and D we can write it in the norm of x minus y, where x belongs to C and y belongs to D. The two sides C and D don't intersect if the distance between them is greater than 0, and they intersect if the distance is equal to 0. And the infimum in the definition is a tangent, which indicates, for example, if the sides are closed and one of the sides is bounded. The distance between two sides can be expressed in terms of distance between a point and a side. You can see it's the distance between C and D. We can write it than the distance in the point of 0 and the side of D minus C. So the result of the previous section can be applied. In this section, however, we derived results specifically for problems involving distance between sides. This allows us to exploit the structure of the sides C minus D and makes the interpretation easier. Now we are going to computing the distance between convex sides. Suppose sides C and D are described by two convex equations, where C has the constraints Fix is no bigger than 0, and the constraints of side D is Gix is no bigger than 0. So we can include linear equation, but exclude them here for simplifically. We can find the distance of C and D by solving the convex optimization by minimize the norm of x minus y subject to the constraints Fi of x and Gi of x. And the alternate distance between the polyhedral, let C and D to be two polyhedral described by the size of linear equation. A1 multiply x is smaller than B1, and A2 multiply x is smaller than B2 respectively, and the distance between C and D is the distance between the closest pair of points, one in C and the other inside D. All the illustrated in the picture. And the distance between them is optimal value of the problem. Minimize the two norm of x minus y subject to A1 multiply x is smaller than B1, and A2 plus A2 multiply y is smaller than B2. We can square the objective to obtain an equivalent problem. And next we are going to talk something about separating convex sides. The deal of the problem to find the distance between two convex sides has an interesting geometric interpretation in terms of separating hyperplanes between the sides. We first express the problem in the following equivalent form. We can set the main problem by minimize the norm of omega subject to f1 of x is smaller or equal than 0, and gi of y is smaller or equal than 0, and I belongs to 1 to I, and x minus y is equal to omega. The dual function we can form as the g function. You can see here. Which results in the dual problem. by maximize the infirm of this form. We can interpret the geometric as follows. If lambda mu are divisible with a positive objective value, then the form is greater than 0 for all x and y. In particular, for x belongs to C and y belongs to D, we have Z transpose multiply x minus Z transpose multiply y is greater than 0. So we see that Z defines a hyperplane that strictly separates C and D. Therefore, if strong duality holds between the two problems, we can make the following conclusion. If the distance between the two sides is positive, then they can be strictly separated by a hyperplane. We can also separate two polyhedron, and we can also define a dual problem in this form. Applying this duality resolves to sets defined by linear equivalence. A1 multiply x is smaller or equal than b1, and a2 multiply x is smaller or equal than b2. We can find the following dual problem. Okay, that's all.